Okay, let's dive right into this explainer and tackle a genuinely fascinating coding challenge, sorting a singly linked list in ascending order. Sorting is such a fundamental operation, right? But doing it efficiently in this specific data structure adds this brilliant layer of complexity that really tests our understanding of algorithmic design. Now, what's really interesting about this problem is the primary constraint. We can't just use our standard array-based techniques, and that's because linked lists completely lack random access indexing. Think about it. With an array, you can instantly jump to index 5 or index 50 in memory. But with a singly linked list, you're forced to traverse sequentially, node by node, strictly following the pointers. This fundamentally changes the rules of the game when you're trying to sort efficiently.
So here is our roadmap for the explainer today. We'll be looking at choosing the right algorithm, the divide and conquer strategy, splitting the linked list, merging those sorted lists, checking out the Python implementation, and finally wrapping up with complexity and stability. Let's start right in with step 1, choosing the right algorithm. So quicksort is usually our go-to when we're dealing with arrays. But without random access indexing, it's kind of a nightmare. Trying to pivot and swap elements efficiently in a linked list just doesn't work out well. That's exactly why merge sort becomes our algorithmic hero here. It processes data sequentially, it relies on breaking things down and then merging them back together, and those are operations that linked lists actually handle beautifully by simply updating pointers rather than physically shifting huge chunks of memory around. Moving right along to section 2, the divide and conquer strategy. Merge sort uses this divide and conquer approach, which really boils down to 3 highly logical steps. Instead of trying to sort the entire massive list all at once, we just split it. And we keep splitting it until the problem is so incredibly small it basically solves itself. Then we just stitch the solutions back together. If you look at this full tree visualization, it makes perfect sense. We start at the top with an unsorted sequence and recursively cut the lists right in half. The base case of our recursion here is incredibly simple. A linked list with just one single node is, inherently, already sorted. Once we hit those single nodes at the bottom, we just work in reverse. We merge those tiny sorted lists into slightly larger sorted lists, bubbling all the way back up to a fully sorted, complete list at the very top. All right, section 3, splitting the linked list. To actually cut the list, we absolutely have to find the middle node. Why? Because the node immediately after it is going to become the head of our brand new second list. But here's the catch. If we don't know the total length of the list, well, actually, we don't want to traverse the whole thing twice just to count it, right? So how do we find that exact midpoint efficiently? We pull this off using the incredibly clever fast and slow pointer technique. Think of it like 2 runners on a track. We advance the fast pointer twice as quickly, hopping 2 nodes at a time, while the slow pointer just jogs along at a steady 1 node at a time. By the time the fast pointer hits the very end of the list, the slow pointer is predictably going to be standing exactly in the middle. It's just a beautifully elegant single-pass solution. Oh, and a quick edge case to note, if the list has an even number of nodes, we just stop the fast pointer when fast.next.next is null, which makes sure the slow pointer lands on the first of the 2 middle nodes. Once that slow pointer lands on that precise middle node, we simply grab the very next node and label it as our second head. This pointer is basically the new starting line for the entire back half of our original data. Finally, to completely sever the connection and create 2 completely distinct lists, we take the middle node's pointer, the slow.next, and we set it to null. This is the structural snip that breaks the original linked list squarely in 2. It allows our recursive functions to go ahead and operate on completely independent halves. Which brings us to section 4, merging sorted linked lists. So these are the fundamental ground rules for the merge phase, and I really want to point out a clever trick here, the dummy node. Think of it as a foundational anchor for our construction. When you're assembling a new linked list, handling that very first node can require a lot of really messy, annoying edge case logic. By just initializing an empty dummy node at the very beginning, we give ourselves a perfectly stable starting point to attach sorted nodes, completely bypassing all that messy logic. We just attach all our sorted nodes onto the dummy's tail, and when we're finished, our sorted list simply starts at dummy.next. Let's actually see this in action. We're looking at 2 sorted sublists. We set pointers at the head of each, so node 2 is on top, node 1 is on the bottom. We compare our 2 lists, see that 1 is clearly smaller than 2, and we just attach node 1 directly to our dummy node.
Because we selected node 1, we advance the pointer on the bottom list over to its next node, which happens to be 5. Now we compare the top pointer, node 2, with the bottom pointer, node 5. This time, node 2 is the winner, so it joins the assembly line, attaching right to the end of our growing merged list.
Next up, the top pointer advances to node 3. We compare node 3 against our bottom pointer, which is still sitting at node 5. Node 3 is smaller, so boom, it attaches. Notice how systematically this threads everything together? It naturally walks down both lists in perfect order.
The process just smoothly repeats itself, attaching node 4 from the top list, which brings us right to the end of that top list. At this point, pointer L1 is officially exhausted. It's pointing to null. Now, once that first list is completely empty, the final rule kicks in. We don't need to do any more individual node-by-node comparisons. Because both original lists were already sorted, if one list completely empties out, literally everything left in the other list must be larger than what we've already merged. So we simply attach the entire remainder of the second list, in this exact case, node 5, directly to the end of our merged list in one swift operation. Okay, section 5. Let's look at the Python implementation. The code here beautifully mirrors the visuals we just went through, breaking down into 3 highly modular helper functions. The main function, sortLengthList, acts kind of like a traffic cop. It checks the base case, like if the list is empty or just one node, it just returns it. Otherwise, it calls splitList to break the list in half using those fast and slow pointers we talked about. It recursively calls itself on those two halves. And finally, it feeds the results into our merge function, which utilizes that super crucial dummy node to stitch the final sorted list together. It really is a perfect one-to-one mapping of the concept straight to the code.
And finally, section 6, complexity and stability. Let's talk performance. Our time complexity sits at a highly efficient big O of n log n. The logic here is pretty ironclad. Every single time we split the list in half, we create another level in our execution tree. Having a dataset of size n repeatedly yields log base 2 of n levels. At each level, we merge all n nodes back together. So log n levels multiplied by n work per level gives us that sweet O of n log n time. Meanwhile, the space complexity remains a really tight O of log n. Since we're just rearranging pointers, we aren't creating massive new data structures or duplicating data. Our only real memory overhead comes from the recursive function calls stacking up in the computer's memory, which is directly tied to the log n height of our tree. Wrapping up here, Merge Sort's absolute hidden superpower is its stability, which means equal elements absolutely keep their original relative order. Imagine sorting nodes that have identical primary values, like maybe a product price, but they have different underlying creation timestamps. A stable sort guarantees that those older timestamps naturally stay ahead of the newer ones in the final list, which honestly begs the question, how much absolute data chaos, overwritten historical logs, and totally disjointed analytics would ensue in global database systems without this crucial mathematical guarantee of stability? It really is the unsung hero of large-scale architecture.